Okay, so let's look at, in this last section of chapter 3, we're going to look at some very simple rational functions. So we already know what rational expressions are from algebra. And so we're going to define a new class of functions to be a rational function if they're quotients of two polynomials. All right, so they're going to be quotients of two polynomials. Right? And so the minute we consider such a function, the first consideration we have to make is the domain, right? We know that a rational expression is not defined when the denominator is equal to 0. And so same sort of thing here. For a function that's of that form, we have to exclude any values that make the domain that make the bottom equal to 0. And so let's go through these. These are already simplified in the sense that there's no common factor in the top and bottom of any of them. And so we want to find where the bottom is 0 to exclude those from the domain. Notice here, if it's already factored like it is here, you set each factor equal to 0 and solve for x. And so for the first one, you had to exclude both 0 and -3 from the domain. And so its domain is everything but 0 and -3. The bottom of this guy factors. It's a difference of squares, where you have 3 squared minus quantity 2x squared. And so it factors as 3 minus 2x times 3 plus 2x. And so you want to exclude anything that makes either of those equal to 0, which is -3/2 and 3/2 respectively. All right. And then finally here, the bottom of this guy is never 0, and because it's already. And so for this one, if it's never 0, if it's the sum of two squares, then there's no restriction on the domain. The domain's all reals. All right, so what we're going to do, we're going to look at how to graph two very simple rational functions, namely 1 over x and 1 over x squared. Those are kind of the basic ones. And then we'll say that if you look at 1 over x squared, or 1 over x to the 4th, 1 over x to the 6th, so on and so forth, just like what was true with power functions, those graphs will resemble each other as closely. And then 1 over odd powers of x will resemble the graph of 1 over x. All right, so we're going to focus only on these two and see kind of what we can gain. All right, so for the first one, there are two things to consider here, right? We know that 0 is not in the domain, but we want to get as close by to 0 as we can to kind of understand what the graph is doing. And so I have a table of values where the inputs are getting closer to 0 from both sides. And I want to get points on the graph for those x values. And then I also want to understand what happens as x gets very, very large in either direction. And that would explain this table. All right, so if you take a look at these values, remember this is a reciprocal function. That's what 1 over x does. So you give it an input, and if you just take the reciprocal of that input, you're getting the y value. And so if I take smaller and smaller inputs here, those are going to result in larger reciprocals. And so as x closes in on 0 from either side, the outputs get either very, very negative if the values of x were negative, or very, very positive if the inputs were positive. All right. Likewise over here, if you take larger and larger x values in either direction, 1 over them is going to get very, very small. Even though these guys are negative and these guys are positive, they're getting very, very small in the sense that the graph, the y value is getting very, very close to the x-axis. And so if you put these two together, excuse me, what we'll have is the following two observations. The closer the input gets to 0, the further the point gets from the x-axis in either direction. It's either going up or it's going down. And the larger the input gets, the closer the graph gets to 0. And so what the graph is, what the graph looks like if we put those together is as follows. The closer the values get to 0 from either side, the larger or smaller in the negative or positive direction the graph gets. And if x gets very, very large that way or this way, the closer the graph gets to the x-axis. All right, now what happens if you look at 1 over x squared, right? We approach it the exact same way as we did before. The only difference now is going to be that values get larger quicker in the bottom, and you no longer have negative outputs, right? Because you're squaring a negative input. And so the tables look very, very similar to each other. It just now, instead of these guys being negative, they're positive, and same way over here. Also notice that I'm squaring this, not just taking the reciprocal, but I'm squaring it first and then taking the reciprocal. And so the outputs compared to 1 over x are actually quite a bit larger. All right. The thing to note is the pattern is the same. As x gets close to 0 from both sides, these guys are both going to plus infinity. They're getting very, very large very, very quickly, right? This is not going to negative infinity anymore like it was for 1 over x. It's going to positive infinity. Same way here, these are both getting very, very close to 0, but quicker because I'm dividing by a large number since I'm squaring those inputs. All right, and so the graph looks like this. All right. In both of these graphs, we're going to call the y-axis a vertical asymptote. It's a line that the graph gets closer to as you approach the input. And we're going to call the x-axis a horizontal asymptote. That's a line that the graph gets closer to for larger values of x in either direction. All right, don't worry too much about this. This is just saying, as we mentioned before, that we only looked at, well, two things. Here, if you considered 1 over x to the 4th or 1 over x to the 6th, the graph will resemble 1 over x squared for the same reason that x squared, x to the 4th, and x to the 6th resembled each other. And the same for the odds, right? So we totally expect that to occur because you're using the same functions here, you're just taking the reciprocals. The same thing works for reciprocals of root functions, right? So these you'll bump into every now and then in the calculus, not very often, but every now and then. And then just realize that if I took cube roots, 5th roots, or 7th roots, they basically resemble the corresponding odd reciprocal function for just the square root and the cube root functions. All right, let's look at this example. So again, we want to use our translation results to our best of our ability to get graphs from the simple ones. And so here we have a translation of 1 over x, and we want to be able to graph it using them. The thing to keep in mind with graphing rational functions is that the asymptotes, both vertical and horizontal, if they happen to exist, move along with the translation. And so remember here, both the y-axis and the x-axis are asymptotes for 1 over x. If you shift the graph left or right, the vertical asymptote will move accordingly. If you shift the graph up or down, the horizontal one will move, right? And so here, to get the graph of this guy, I'm going to first move 1 over x to the left 3 units. That means that the vertical asymptote is now going to move from the y-axis, which is x equal to 0, to x equals minus 3. And notice that also is the x value that makes the bottom 0. Right? And then we're going to move that graph down 2 units. So the horizontal asymptote is going to move from y equals 0 to y equals negative 2. All right, and so let's jump to the graph. The graph looks, the graph looks like this, where the asymptote is going to occur here and there. All right. In terms of the y and x intercepts, if you plug in 0 for x, right, you're going to get 1/3 minus 2, which is minus 5/3. And to find the x-intercept, if it exists, we basically want to set this function equal to 0 and solve for x. And so that's where your solving rational equations comes from back in your algebra. All right, so to solve this, I'm going to add 2 to both sides. Then I'm going to multiply both sides by x plus 3, distribute the 2, and then I'm going to subtract 6 and divide by 2. All right, so I get x equals minus 5/2 as the x-intercept. Okay. Once we have the graph, we want to know about increasing, decreasing, values where it crosses y equals 4 in the inverse. All right, so notice that the graph is never increasing, right? If you always move from left to right, these values dip down and they always dip across. So they're always decreasing as you move from left to right, except for at the asymptote. But remember, the asymptote's not a point on the curve, and so you can't include it as a point in an interval where you're talking about increasing and decreasing. Otherwise, there'd be a point of contention right at the asymptote. So it's decreasing entirely to the left of -3 and also increasing entirely to the right, decreasing entirely to the right. If you want to find where this function hits the line y = 4, y = 4 is a horizontal line, right? And so to find the intersection of any two graphs, you set the two functions equal, which means we want to set the rational function equal to 4 and solve for x. We solve that for x in exactly the same way. We add 2 to both sides and then multiply by x + 3. But if you do that, you distribute the 6 through, subtract the 18, and then divide by the 6. Right, so the point of intersection, that's the x coordinate. To find the y, you put this into one of the two functions up here, but that function's constant, right? And so we know the y coordinate has to be 4. Finally, is this function invertible? No, the answer is yes. Even though these look like they're horizontal, they're not. They're constantly getting smaller, although the rate at which they're doing so is getting very small. Right? But nevertheless, the graph passes the horizontal line test, and so it's 1-to-1. That means it's going to have an inverse. So what we do is we set y equal to this guy, interchange the x and the y, and we want to solve this for y. So I'm going to add 2 to both sides, and then I'm going to multiply both sides by y + 3. Remember, I need to isolate the y term, and so I'm going to distribute, or if you think about foiling it out, but I just distributed the x + 2, the whole quantity, through both these terms. So I multiplied the y by it, multiplied the 3 by it, and then I just took this whole term to the right. I subtracted it, right? Distribute 3, and combine the -6 and the 1, and then I just divide by x + 2. Doing that saved me from having to factor later, right? That was the only reason. But you could technically have approached it slightly differently. All right, so this function here is the inverse function for that guy. Right? So if you were to graph this function and this function on the same set of axes, you would notice that they are reflections of each other over the y = x line. All right, now for the your turn, you're doing the same thing, but now with a 1/x² function instead of the 1/x function. All right, so give that a go and see how it goes, and then we'll talk about that. All right, so let's take a look. You're going to use 1/x². We're going to shift it to the right 4 units and then up 2. Right, that's what, from just using our translation results, that's what we would do. And so we know that the vertical asymptote that occurred at x = 0 now will occur at x = 4. And since we moved it up, the horizontal asymptote will now occur at y = 2. In terms of the y-intercept, you're going to plug 0 in for x, right, to get that number. So plug in 0, you get 1/16 + 2. That's 33/16. And then to find the x-intercept or intercepts if they exist, you set this equal to 0 and solve for x. The thing is, though, if you set that equal to 0 and you try to solve for x, you'll have to first subtract the 2 from both sides. But at this point, notice that the left-hand side is always positive, right? It's 1 divided by the square of something. That's never even 0. It's always positive, yet the right side is negative. And so what that tells you is that this equation has no real solution, and so there are no x-intercepts for the graph. If you look at the graph, that makes perfect sense, because remember, 1/x² originally was always above the x-axis, and we've moved it up, right? And so it's always above the x-axis, which means it doesn't have an x-intercept. Okay. In terms of increasing and decreasing, remember, you always move from left to right. And so it's increasing up until you get to that vertical asymptote at 4, and then it's decreasing to the right of that vertical asymptote. To find where this function hits the graph of the line y = 6, you set them equal to each other. right? And so y equals 6 is up here. We know that that horizontal line will actually hit the graph twice. And so we expect a quadratic with 2 solutions. Let's see what happens. If you set them equal to each other, to solve for x, I'm going to subtract 2 from both sides. I'm going to multiply both sides by the denominator. Let me just increase the size of this to get this equation. I'm sorry, this one. Now I'm going to take the square root of both sides, right? To avoid fractions, I'm doing the square root now. So you get plus or minus 1 on the left, and on the right, you just get the square root of that guy, which is 2 times x minus 4. Remember, you only put the plus or minus on one side, and the side that you put it on should be the one that does not involve x. That's why I'm putting it on the left side. To solve for x, distribute this 2 through, add 8 to both sides, and then divide by 2. Right, so you'll get 2 solutions, namely 7/2 and 9/2, and they're going to be equidistant on either side of the vertical asymptote because the graph is symmetric about it. Right, so you get 2 points of intersection. And then lastly, that was an example of a horizontal line that hit the graph in 2 spots. And so that proves the function's not one-to-one. And so it does not have an inverse on its domain. All right. A couple of observations, just last minute observations here. In terms of polynomials, we know that polynomials have a domain of all reals. And so there's never a break in the polynomial's graph. And so a polynomial can never have either a vertical or a horizontal asymptote, right? Vertical asymptotes would occur when the bottom is 0. Well, there is no bottom for a polynomial function. And the horizontal ones would occur to describe the long-term behavior. But remember, we have a classification for long-term behavior in terms of the term of highest degree for a polynomial. It's either going to behave like a negative or a positive x squared or a negative or positive x cubed. And none of those follow an asymptote, right? So it's important to realize that for a polynomial, that will never actually occur. All right, you could do a lot more with rational functions. We could look at functions where they aren't translations of one of these, but that would take us further afield of what we really want to do, and that's to gather a general toolbox for calc. And so we're going to stop there with the rational guys. You'll study the graphs of more general rational functions in Calc 1 later on. But that's kind of a brief exposure for you. All right, so for homework, go ahead and try these problems. Again, we're starting to mix things together, so it'll appear to be more complicated, but just go back to the toolbox, right? Remember what these things mean to do. The fact that I'm adding in new types of functions doesn't change how you attack them, right? The attack is still the same as it was in chapter 1. All right, give those a go and let me know how it goes. All right, bye.